Okay, this is a video on section 6.6, standard enthalpy of formation and reaction. Now, we're going to have to break this down into a couple of videos. This one's going to be about 10 minutes or so. The next one should also be about 10 minutes or so. And that should take care of the entire section with basically 2 videos. So, my friends, you learned in the last video that you can use the method of calorimetry in order to find the heat of a reaction, right? So this is an experimental method used to find the heat of a reaction, or in other words, the delta H of the reaction. So does that mean that every time we want to find the delta H of a reaction, the heat of reaction, we would need to do a calorimetry type experiment? That would be a pain if that were the case, okay? So why do I even ask this question? I mean, why would I say this? Is there another way of doing this? Well, my friends, you know that delta H, the enthalpy change, is a state function. And being a state function, it should be equal to the H of the products minus the H of the reactants. There's a problem associated with this equation. We don't know what the absolute enthalpy of the products and the reactants are. Remember, we can never measure the enthalpy, the absolute enthalpy of a substance. So we can't know the absolute enthalpy of the products, and we can't know the absolute enthalpy of the reactants. And so even though delta H is a state function, and it's dependent upon the initial and the final states, we don't know what the value of the initial and the final states are. And therefore, we can't find the delta H that way. Well, geez, that's kind of a pain in the neck, I would think. And it is. What we can do, though, is this. We can't know the absolute enthalpy for a particular substance, but there is an enthalpy in particular that we can find for a substance. In particular, it's an enthalpy change. It's an enthalpy a change that occurs when the substance is formed. So we call it the delta HF, or delta H of formation. It's defined as the enthalpy change that occurs when 1 mole of a substance is formed from its elements. Oh, hey, that's good. We can now know some type of an enthalpy for a substance because we can determine what the delta H of formation is for a substance, and it would be nice if we can use them and compare them to each other and try to hopefully use that to find the delta H of an entire reaction. Well, we want to be able to use them to find the delta H of an entire reaction. We want to be able to use them to compare them to each other. So they really should be measured under the same set of conditions. So if we set the conditions to what are known as standard conditions, 25 degrees Celsius and 1 atmosphere of pressure, then we put this little symbol here which is called naught, and it's the delta H of formation, and we call it the standard enthalpy of formation. And as you can see in the background at the top of this table, you see that this table is called the standard enthalpies of formation of some inorganic substances at 25 degrees Celsius. So here, measured behind you, are the enthalpy of formations, right? The enthalpy change that occurs when 1 mole of that substance is produced from its elements under the standard state conditions. And they're all measured under the same set of conditions so that they can be compared to each other, so that they are relative to each other. And so, my friends, let's talk a little bit about those values. If we look at them, let's get rid of some of this other stuff here. If we look at them, let's make it a little bigger. Woof, there we go. If we look at silver, silver has a heat of formation of 0, but silver chloride has a heat of formation of negative 127. And aluminum has a heat of formation of 0, and aluminum oxide has a heat of formation of negative 1669.8. And bromine has a heat of formation of 0, and HBr has a heat of formation of negative 36.2, excuse me. And you might come to the conclusion that, hey, silver and aluminum and bromine, well, they're elements, and they have heats of formation of 0. But if you look at graphite, well, graphite has a heat of formation of 0, but diamond, which is also carbon as well as graphite is, has a heat of formation of 1.90. There's something to that, my friends. It turns out that the heat of formation of an element is 0 if the element is in its most stable state. The heat of formation of an element is 0 as long as it's in its most stable state. Graphite is the most stable state of carbon, and it has a heat of formation of 0. whereas diamond is not. If we look over here to oxygen, you see O2 is the most stable state of oxygen, and it has a heat of formation of 0, whereas O and O3 are not the most stable states, and they have heats of formation, and you can see that O has an even higher heat of formation than O3. And we notice that some of the heats of formation are negative, which means the process is exothermic, and some heats of formation are positive, which means the process is endothermic. So, what do we do with these heats of formation? Oh, well, I'll tell you. It turns out, my friends, that these heat of formation can be used like they were absolute enthalpies. These heats of formation can be used if you have a reaction in which A with a coefficient of A reacts with B with a coefficient of B to form C with a coefficient of C plus D with a coefficient of D, the delta H of this reaction, RxN is what the cool kids call a reaction, RxN, measured under the standard state conditions, is equal to the sum of the heats of formation of the products measured under the standard state conditions minus the sum of the heats of formation of the reactants, also measured under the standard state conditions. So we can use the heats of formation to find the delta H of reaction, but only when it's measured, or when they are measured under the same conditions. And that's important because, well, we can't find the delta H under any other conditions this way. But, you know, most things happen at 25 degrees Celsius and 1 atmosphere of pressure in the world of chemistry. And so, it's good enough. So, if we take this equation now and expand it to the equation above, we'll see what the values of N and M are, because you were probably looking at N and M and saying, what the heck are N and M? He didn't mention N and M. What is wrong? So, let's find out what N and M are all about, okay? I'll show you. If we take this equation and break it down for the equation up above, it becomes that the delta H of the reaction is going to be equal to the coefficient of A times the heat of oh, goodness gracious, I almost did it. Very close. Remember, it's products minus reactants. I was doing reactants minus products. So remember, it's products minus reactants. So it's the coefficient of C times the heat of formation of C under the standard state condition plus the coefficient of D times the heat of formation of D under the standard state conditions. And we're going to add those two up, and we're going to subtract from that the coefficient of A times the heat of formation of A under the standard state conditions plus the coefficient of B times the heat of formation of B under the standard state conditions. And that's where the N and the M come in. The N and the M represent the coefficients. So remember, heats of formation, like any other delta H, are technically measured in kilojoules per mole. So we have to multiply the value times the number of moles of that particular substance in the equation, which is the coefficient. So for the reaction A with a coefficient of A plus B with a coefficient of B, reacting form C with a coefficient of C and D with a coefficient of D, the delta H of the reaction under the standard state conditions can be determined by taking the heat of formation of C and multiplying it times the coefficient, adding to that the heat of formation of D times its coefficient, and subtracting from that sum the heat of formation of A multiplied times its coefficient plus the heat of formation of B multiplied times its coefficient. And so, my friends, let's see if we can do a quick example to try to make this short. Try to make this a short problem and make this video a short video. We don't want it to be too long. Okay, so here is the problem. And this is in your text, and it's on page 259 at the bottom. So if we have two aluminums, whoops, put that back, whoops, too many whoopses. Okay, good. If we have two aluminums and it reacts with Fe2O3, and that is a 3 there, and it's formed Al2O3 and iron. This is known as the thermite reaction. We'd like to find the delta H for this thermite reaction. Now, all of these delta H's of formation can be found in your appendix in the back of the textbook. But the delta H of this reaction under the standard state conditions is going to be equal to 1 times the heat of formation of the aluminum oxide. Oh my goodness, this is such a mess. I apologize. This is very messy. Tell you what, because this is messy and you would probably be better off trying to look at this, why don't you look at the example on the bottom of page 259 until I get a stylus. Once I get a stylus, then it won't be so bad. But I will. I'll get a stylus. Anyway, that's the video. That's as far as we want to go with this. We're going to show you another method in the next video, an indirect method for finding the delta H of a reaction. So take a look at that example, try some problems, and ask questions, and we'll see you in class tomorrow. Or Mr. Walsh will see you in class tomorrow. Maybe I won't see you at all. Okay, bye.